Okay, now we can talk about some different complexity class, not quite complexity classes, but like computability classes. So there's different levels of how undecidable problem is. So for example, if a set L is recursive, that means there exists some Turing machine M, such that you feed it some input X, and M will accept if X is in the language, and M will reject if X is not in the language. So note by definition, for all inputs X, M of X holds. So if a set is recursive, we can think of it as being there will always be some finite decision process, some algorithm that you can take an element, you can take some string X, and it will definitely check whether that string is in the set or not. So for example, a set that is recursive could be the set of all strings of zeros such that there's a prime number of zeros. This would be an example of a language that's recursive, because obviously there exists an algorithm to check if a number is prime or not. Okay? This is what we call decidable. So decidable problems are one where the set of all strings X that satisfy some predicate P that's a recursive set. So things that fall into this category are called decidable. Undecidable problems, well, there's different levels of undecidability. So the first level is recursively enumerable. So a language or a set of strings L is recursively enumerable if there exists some machine M such that language of M is L. That is to say, the set of all strings that M accepts is L. Equivalently, if the string is in the language, then M of X accepts. And we make no guarantees about the behavior if it doesn't accept. So if X isn't in the language, then M could halt and reject, or it could not halt and run forever. What it can't do is halt and accept, because that would mean X is in the language. So M may not halt for things not in the language, but if it does, then it has to reject. An example of a language that is recursively enumerable is the language we talked about earlier. The set of all encodings of Turing machines M and strings W such that M accepts W. Because if a tuple is in this set, I can check that by just running M on W, and if M on W halts, then if I run it for a while, eventually it'll terminate and then accept. So if a tuple is in this language, I can verify that fact. But if it's not, I might not be able to, because M could run forever on W, then I get stuck. Okay, so we usually call this L sub E. Just to stick with the notation. Co-recursively enumerable. A set L is co-recursively enumerable if the complement is recursively enumerable. Equivalently, there exists some machine M such that the language it recognizes is the complement. So equivalently, if X is not in the language, then M of X accepts. The set of all strings that it accepts is things in the complement of L, so that'll be strings not in L. So if a string is not in the language, then M will accept it. If the string is not in the set L, then M will accept it. And if a string X is in the set L, then we make no guarantees about the behavior. So this is like the opposite of co-recursively enumerable. Okay? Well, clearly an example of a co-recursively enumerable set would be the complement of L sub E, because L sub E is recursively enumerable. So we can imagine these classes of languages laid out like this, but it happens to be the case if you live here, if you're recursively enumerable and co-recursively enumerable, it happens to imply that you are indeed recursive. So we should actually draw these sets like this. In the next video, we'll go through a proof that recursively enumerable intersect co-recursively enumerable is exactly the language, the set of all recursive languages. So when we say RE, we mean like the set of all recursively enumerable languages. So we can treat these things like sets. So if you're a member of RE intersect co-RE, that is to say, if you're both recursively enumerable and co-recursively enumerable, that's the same as being recursive. So we'll do the proof of that in the next video.